Next, we will going to prove the necessary part of Neyman-Pearson fundamental lemma. Okay. Let phi star of x be a most powerful test at level alpha for testing h naught versus h1, and phi of x be a test satisfies condition 1 and 2. Okay, here let phi star of x be a most powerful test at level alpha for testing h naught versus h1, and phi of x be a test satisfy condition 1 and 2. It will take A, okay, set A be a set which intersection of A1 union A2 with the set of phi of x and phi star of x differs. That is A equal to we will write, let A be a set which is intersection of A1 union A2 with the set phi of x and phi star of x differ. That is f1 of x is not equal to k into f0 of x, right? Then we can write A as equal to A1 union A2 intersection of the set phi of x and phi star of x differ. That means f1 of x is not equal to k into f0 of x. So we can write it as x f1 of x not equal to k into f0 of x, right? And here in this case we can assume that a measure on A is greater than 0. Okay, so here we will assume that measure on A is greater than 0. Okay, which implies mu A is greater than 0, right? Which implies, so in the previous proof we know that measure is greater than 0, then we can write it as integral over phi of x minus phi star of x into f1 of x minus k into f0 of x is here mu. Measure, right? Measure A. Then d mu A is greater than 0, right? Here measure on A is greater than 0, then this term is greater than 0, right? From this term it will implies that phi of x is most powerful test than phi star of x, right? We proved that in last part, right? This term implies that phi of x is most powerful test than phi star of x, right? So which implies phi of x is the most powerful test than phi star of x, right? This condition, this is a contradiction, right? Because we started from phi star of x be a most powerful test, right? So this contradiction is due to our assumption, right? Assumption due to measure A is greater than 0, right? From this assumption, right? So this is a contradiction because I started as the phi star of x is a MP test. This is a contradiction, right? So A equal to alpha. Sorry, A equal to 0, right? That is over a set measure on A equal to 0, right? So here this contradiction due to our assumption measure of A is greater than 0, right? Which implies phi of x and phi star of x are same test, right? Hence phi star of x satisfies condition 1 and condition 2. So this is a contradiction, right? Because we started from the phi star of x be a MP test, and also phi of x be a test which satisfy condition 1 and 2, right? Then we assume the measure 1 is greater than 0, which implies that phi of x is a most powerful test. That is wrong, right? Because it's a contradiction due to measure of A is greater than 0. So if measure of A equal to 0, then phi of x and phi star of x are same test, right? Then if phi of x and phi star of x is the same test, then phi star of x satisfy the condition 1 and 2, right? Here it says that phi of x be a test satisfy condition 1 and 2. If phi of x and phi star of x are same test, then phi star of x is satisfy condition 1 and 2, right? Hence the proof. So in this part, what we done is that if there is MP test, it must be same as the test which satisfy condition 1 and 2 almost everywhere. Okay, that is over a set measure 0, you may modify the things here, right? This is the proof of Neyman-Pearson fundamental lemma. So in Neyman-Pearson fundamental lemma gives the entire condition under which you can derive a MP test uniquely up to almost everywhere. Okay, so in Neyman-Pearson fundamental lemma, which gives entire condition and which you can derive a most powerful test uniquely up to almost everywhere. So this is Neyman-Pearson fundamental lemma. Okay.